so let's talk about text-to-speech synthesis, TTS. So there are lots of papers that use transformer architecture for text-to-speech modeling. And of course, there are other approaches as well. And WaveNet, created by Google, and fast speech is very popular. What else is popular? This one is a bit popular. And the rest of them are really interesting. All of them are interesting. But in 2019, this paper came, Mel-GANs. So in all of these paradigms, let's say, we have some articles that just transform to a Mel-GAN, Mel spectrogram, from text to Mel. And the other set of algorithm are for the rest of that. I mean, from Mel spectrogram to the actual audio. So let's come back and see. So there are some algorithm that transform from text to Mel spectrogram, because we have a sequence here, we have a sequence here. That's why this here should be recurrent neural network, LSTM, transformer, and those things. And from Mel spectrogram to the actual raw waveform, we could use different algorithm, but for different purposes. So if we combine these two sets of algorithm, we can come up to text-to-speech synthesis. And this one is a really important article. So we want to so after normalization, what is normalization? For example, you have in text, you have doc, it means doctor. So it normalizes to the word doctor. Or January, it understands that it should pronounce January. So this is a bit normalization. And then we have, so we transform genome from genome to phoneme, and then we have waveform blocks, and that's it. So we first convert text to intermediate representation. By intermediate representation, I mean something like Mel spectrogram. And then from Mel spectrogram to the actual audio. So here is short-term Fourier transform, and then the other way, the inversion is called vocoding as well. So it is inverse short-term Fourier transform. So as I said, there are articles for text conversion of text to Mel. We call it text to Mel models. For example, Fast Speech 2 is one of them. Of course, my favorite is Transformer TTS. And in this lecture, we focus on this approach. For neural vocoder, you could use a parallel WaveGAN, you could use WaveNet, you could use WaveNet is for Google, it's very popular, but you will see that models like GANs are little explored. So you could use pure signal processings, I mean something like inverse short-term Fourier transform. You could use autoregressive neural network, but they have some problem because they are so slow in inference. Because they should generate all of these sequentially, so it takes time. That's why people talk about non-autoregressive models. I mean, they are still using it because they are only taking advantage of knowledge distillation. So they distill and already trained autoregressive decoder into a, for example, flow-based convolutional student model. And there are little papers about GANs, although we have used it for text, images very successfully. So why not for speech? So this is the motivation. So we have Mel spectrogram. So we have a kind of estimated MAGA spectrum, kind of inversion. Like, of course, you can combine it with inverse short-term Fourier transform write your own article, your own algorithm. And here we have a discriminator that says if it is real or it is fake. If it is, for example, the voice is very similar to the voice of your friend or not. And this is the generator. And then finally, this is the Mail-GAN model architecture. We have convolutional layer, then upsampling, residual stack, as we had in different lectures. So finally, we get the raw waveform. So I said Mail-GAN is just conversion of mail spectrogram to the raw waveform that we would like to hear, that we understand as a human. And we have the discriminator and generator. And the residual stack is like this. And of course, there are other models as well, because it is a sequence-to-sequence model. So we need some kind of, we should either use LSTM or we could use transformer models. So Tacotron 2 uses LSTM. And here it uses bidirectional LSTM. And fast speech 2, which is the faster approach for fast speech, uses a variance adapter. And of course, for example, a woman, for example, has a high pitch, and men usually have low pitch. And using these variables, you can also learn these energy, duration, in order to capture the voice correctly. And finally, LAS transformer is just for speech recognition, but we should focus on this article in 2019. So we use transformer. Why do we use transformer? Because we usually do it for sequence-to-sequence model, like text to mail spectrogram. And then we say that, for example, we predict which one has the highest probability, because still is a sequence. And so it's just a transformer architecture, but the inputs and outputs are text and mail spectrogram. And finally, if they combine with each other, they complement each other, they marry each other, and this is their kit. And of course, I will upload it in GitHub, my code in GitHub, so that you can go through that and check the details. And I've had my results for a long time, but I do not yet know how I am to arrive at them. Carl Friedrich Gauss.